We are now in Chapter 9, where we will explore the concepts of scatter diagrams and linear correlation. Suppose now that for every value of a variable x, we know a corresponding value of a variable y. So this set of ordered pairs, right, you have an ordered pair xy, that's called a bivariate population. And you probably remember from algebra that an ordered pair looks like this, where the input variable is written first and the output variable is written second. Order makes a difference. Input first, output second. So there's two questions that naturally come up with this. First of all, is there a relationship between these two variables? And secondly, if there is a relationship, how can we express it mathematically? How can we express it by means of an equation? For example, can a low barometer reading be used to predict maximum wind speed of an approaching tropical cyclone? So what we're going to do here is this. For a random sample of tropical cyclones, let X be the lowest pressure in millibars as the cyclone approaches, and let Y be the maximum wind speed in miles per hour of the cyclone. So we're going to get some ordered pairs here. We're going to match up lowest pressure to wind speed. So we're going to get this set of, looks like 6 ordered pairs. So this matches our question 1, which was, is there a relationship between the two variables, in this case x and y? So here's the start of our solution. We're going to construct what is called a scatter diagram. And a scatter diagram is just a graphical representation of a set of data pairs in a coordinate system. So we're going to draw an x and a y axis, just like you did in algebra, and we're going to plot these pairs. Now, here's our ordered pairs, x and y. X is our input, y is the output, but we have statistical names for these. X, our first component, is called the explanatory variable, and y, the second component, that's our output, that's called the response variable. We choose these terms because effects in the response variable are explained by changes in the explanatory variable. Here's a picture. Here's our x. Here's our y, right? An ordered pair, x on the left, y on the right. And what we're going to do is we make changes in this variable here to observe the effect on this variable over here. So this variable here responds to changes in this variable here. So this values of this variable explain the effect or changes in this variable here. But as I start to draw my axes, I notice this, that the x's, they are high numbers, right? They really, like the lowest one is in the 900s. So I don't want to start the x's at 0. I'd have a bunch of blank space. And the y's, they start at 40 and seem to go up. I don't want to start that at 0 either. I'd have a lot of blank space. So when I draw my axis, I'm going to draw them big, and I'm going to do this. I just put these little breaks in it to tell the reader that we're not starting at 0. Now, we're going to do this one by hand, so it's a little bit more work than we'd have to. Typically, we just have the computer do it, and the computer would determine, okay, what kind of intervals do we have here and here? But we're going to try it by hand. So I noticed this, that look at the y's. They go from 40 up to 100, 100, okay. The lowest is 40, the highest is 150. But if I went 40, 50, 60, that'd be a lot of them. So how about if I just go every 20? So maybe I could go like 40, 60, 80, 100, 120, 140, 160. I seem to have just gotten it. So 40, 60, 80, 100, 120, 140, 160. Now, this is just a picture. It's not really meant to be totally accurate. It's just to give us an idea, a feel for what's happening. Now, look at the x's. They go from where to where? The x's, I got 1,000 here, and they go down to about 900. How about if we just did this? What if I start this at 900 And then if I just went up maybe every 25, so 900, 925, 950, 975, and 1,000. Now, as best we can, we'll try to plot these points. So we've got a point here at 1,004, so out to 1,004, up to 40, all right? So x is 1,004, that's maybe like right here, and up to 40. Maybe that's right here, all right? So let's draw that just as best we can. 1,000, I don't need all that. 1,040, maybe it's right there. The second point is at 975 and 100. Okay, well that's nice, it's kind of right on our graph. So it's 975 out this far, and up here at 100. So I'll put a point there. 975 and 100. Then I've got 992 and 65. So let's see where that's going to be. 992. Well, 992, that's probably in here somewhere. And 65, that's probably up right around there. So 992 and 65. Let's see, I'm thinking, well, maybe here. Okay, make a big dot, that'll cover it. Then 935 and 145, so 935, where's that going to be? 935, maybe here. 935 and 145, so 145, maybe up here. Let's get that, 935 and 145, that's probably like here. Then we've got the 985 and the 80. Now 985, maybe here, and 80 up here. So 985 and 80, maybe like this. And then the last one, 932 and 150. Now 932 is going to be around here, and what was it? 150. That'll take us up to almost the top there. So 932 and 150, maybe it's like right up here. 932, something like that. Well, that's a little bit too high maybe. Well, it's close enough. Now we look at our picture and there seems to be some kind of pattern here. These points aren't just all bouncing around all over the place. There seems to be some kind of a structure. So a couple things here. If the points seem to lie near a straight line, as ours do, right? They're not all exactly on a straight line, but they're kind of near a straight line. All right, then the correlation is called linear. So what we're working with here is called linear correlation. Now, if y increases as x increases, now x increases, remember we're going horizontally to the right, and y increases means that we're going vertically up. So look at your picture here. Put yourself kind of at the zeros. If as x increases, the y's are increasing, this is called a positive correlation, like you have positive slope. Now, if on the other hand, y decreases as x increases, so put yourself here, as x increases, y decreases, this correlation is negative. Negative correlation, negative slope. And that's what we have, right? As you start here, as you increase the x's, as the x's increase in value, go to the right, the y's are decreasing in value. They're going down. Now, if your points on the scatter diagram lie near some curve, the correlation is called nonlinear. Now, we're not going to take a look at nonlinear correlations in this course, but a nonlinear correlation might be something like this. Suppose you plot your points and you get something that looks like, okay, maybe you get something that looks like this. Okay, now there's definitely a pattern going on there, but it's not linear. And it looks like we could maybe pass a parabola through these, so you might have something like a quadratic relationship. And then finally, if the points in your scatter diagram are just all scattered about with no apparent structure, then there is no correlation. So for example, what if you draw your scatter diagram and you get, something like this, right? There's no apparent structure here. So we would just say no correlation. And now, if a linear correlation does exist, as we think ours does, we want to measure its strength. Is it a strong relationship or is it kind of a weak relationship? So the measure, there's a name for the measure, is called the coefficient of correlation. We use the word coefficient here because the word coefficient means kind of how much of something you have. You remember back in algebra, you might have said something like this: what if you have 4x? So what do you have? You have 4 x's. So the 4 is the coefficient, and it tells you how many of these things you have. So how much correlation do we have? Well, that's going to be measured by the coefficient. So here's our definition. The coefficient of correlation, now we use a lowercase r. Now this is an English letter because it's coming from a sample, right? This is just a sample of values. So the coefficient of correlation r is a measure of the strength of the relationship between the two variables. The value of r will always lie between -1 and 1. So r, the coefficient of correlation, the measure of the strength of the relationship, will always be between -1 and +1. When r equals +1, right over here, that's called a perfect positive correlation, and all the data points, all your ordered pairs will line up exactly on a straight line with positive slope. And an r value of -1, that's this extreme, r value of -1, that's called perfect negative correlation, and all your data points, all your ordered pairs will lie perfectly on a straight line with negative slope. And then right in the middle, if r is 0, there's no correlation, and your data values, your ordered pairs, would just be like scattered all over. No apparent structure. And then it follows that the closer r is to 1 or -1, the stronger the relationship. And the closer it is to 0, the weaker the relationship. Here's a formula for computing r. Suppose you've got n ordered pairs, then r is equal to, well, you make this computation. Now, you have to look closely in here to see what it is that we're doing. Let's just see if we can get a little glimpse of what it's telling us. When I look at the formula, I see I'm taking the difference between a data value and the average of all the x's. Now that tells me how far apart this value is from this one. How far from the mean is this value here? The same for y. How far from the average of the outputs is that particular output? And then I add up all those discrepancies. And then I divide by, maybe you can see a standard deviation in here. All right, now this is an inconvenient form to use. So here's a better, more convenient form, although not as convenient as just putting it in on your calculator. But here's a more efficient computing form. Now, if you manipulate this algebraically, like multiply all this out, change the x bars into the summation of x over n, change the y bars into sum of y's over n, do all that algebraic manipulation, you can convert this top into this top. And the bottoms, well, look at the bottoms. Do you recognize this? You have to go way back to the beginning of the course when we did one variable statistics. We found the standard deviation using formulas like this. Here's the standard deviation of the x's, standard deviation of the y's. Now I'll just tell you, in our problem, r is equal to positive 0.95. We'll actually compute it later. Now remember, r, that's a measure of the strength of the relationship between the two variables. So the value of r, once we compute down here, say, and we get a value for r, like our 0.95, that value of r should help us decide if there is or is not a relationship. So here's a picture of the way I see it. Here's my r's. The r's are going to go from -1, here's 0, all the way up to +1, right? So the r's go from -1 all the way up to 1. Now, if r is 0, there's no correlation. But it doesn't have to be exactly 0. If it's just close to 0, I'm going to say no correlation. Well, how close do I have to be? Or how far away from 0 do I have to be before I say there is a correlation? Like, okay, no correlation, no correlation, no correlation. Now I finally get out far enough that I say, okay, we're far enough from 0 that we're going to say there's a correlation here. So if r, your value of r lands in this interval here, we're going to say there's a correlation. If your value of r lands somewhere in this interval, we're going to say there's a positive correlation. But if R is here, we're going to say it's too close to 0, no correlation. So this point here and this point here, these are called decision points. And decision points, those are based on the size of the sample. And we're going to do this by running a hypothesis test. We know all about hypothesis tests. So what we're going to do is we're going to run a hypothesis test on, now we run test on parameters. This is the corresponding parameter. The English letter is R, so R, R-H-O. We pick a Greek letter that starts with R. It's rho, kind of looks like a lazy P. So we're going to be testing this. We're going to test that H naught states that rho is 0, or some version of that. Let's find R with our cyclone example. So I've got the data right up here. So we're going to run a test on this, a hypothesis test. But what we've got is data, right? We have data. We don't have the statistics yet. So we have to put the data into our lists. So you probably remember how to do this, but just in case, you press the stat key, and then you go to Edit. Let's find the value of R using our cyclone example. Got the data right here. So we're going to run a hypothesis test, but we're not given the statistics. We're given the data, so we're going to have to put the data into the lists. So remember how to do it. You press the stat key, and then you select, just comes up, you select number 1, which is Edit. Then all your lists come up. I think there's 6 of them here. But if you have data in there already, we need to clear that data. So to clear the data, take your cursor and put it right on, get it over here and maybe to the left and up, get it right on the L1, right? So use your left cursor, left arrow, and up arrow, get the cursor, now if the number's here, get it over and then up, right on L1, press clear, all right, so then you're going to press clear. All right, press clear and enter. And then all that data is gone. Now, once you've got that data gone, we need a list 2. So right arrow over to list 2, all right? So your right arrow to list 2 and then up so that your cursor is right on L2. And then press clear and enter again. Then all that data is gone, right? So you've now cleared out all of the data. L1, L2 are blank. Doesn't matter what's in L3. We're not going to use that here. Now get your cursor back in L1 and put in the L1 numbers, all right? These are the X values. So you're going to put in 1004, enter, 975, enter, 992, enter, 935, enter, 985, enter, and 932, enter. Now you've got those in. Now right arrow to L2, and that will bring you right at the top, right up there. Put these numbers in. These are the Y values. How about 40, 100, 65, 145, 80, and 150. All right, now be sure to press enter after that 150 so that it accepts it. Now, just as a note, just because I've done this before, suppose that you forget the 150 and then you try to run the statistics on it, you're going to get what's called like a D-I-M, a dimension error. You get an error in dimension because the dimension of the first column is different than the dimension of the second column. So if that comes up, you know you probably missed a piece of data. So you go back in and you find out, okay, what did I miss? But make sure when you put these in that they're aligned, right? This 1004 goes with the 40, the 975 goes with the 100, and so on. So I got to make sure they are lined up. Now you've got your data in. So now go back to that stat key. This time we want to scroll over to tests. We're ready for our test. And now what you have to do is you have to scroll down to the proper test. So you can scroll down all the way to F. F says linear regression t-test. Once you've used this for a while, you'll see instead of scrolling down to F, you could scroll up because F is nearly at the bottom already. When you select F, what comes up is this. What's your X list? What's your Y list? What's the frequency? What is beta and rho? We'll talk about those. But your X list, this is L1. So L1. So remember how to get L1. You press second. I'll do it down here at the very bottom. You press second and the numerical key 1, because right above 1 is L1. All right, so you get L1, press enter, L2, so second, number 2, you get L2. Frequency is 1. Each one of those numbers in each list appears only once. Let's set up the hypothesis test so we can complete our table here. H naught and H sub A. Now, what is it that we're looking at here? Right, the first sentence, can a low barometer reading be used to predict maximum wind speed? So we want to know, is there a correlation between the barometer reading and the wind speed? Correlation, yes or no? So I just like to do this one first. So I'm going to say that rho, now that's the parameter that we use, a Greek letter, I'm going to say that this is not 0, right? That means that rho, the correlation coefficient, is not 0, which would mean that there is a correlation, right? Remember, if we're far enough from 0, remember how this goes. If we're out here at -1, +1, at 0, if we're close to 0, we've got no correlation. So we're going to test the fact that it's not 0, that it's out here or here, that there is a correlation. All right, so if this is not 0, up here, that's just the opposite. So that's going to be rho equals 0. So now down here on my test, I've got the X list, L1s, the Y list, L2s. The frequency, each piece of data appears only once. Now what do I want here? All right, we're not really talking about betas, we're talking about rhos. So I want rho to not equal 0. So I'm going to select this one right here. So get your cursor over onto that one. Now I'm going to skip this regression equation. It really gets built in. We don't need it. Just leave that blank and go down to calculate. Now when you calculate, here's what your screen looks like. You've got y equals a plus bx. Then you've got beta not equal to 0 and rho not equal to 0. That's what we're testing. Then you've got this t star value. That's really our computed value if we were doing it with the critical region approach, -13.85, ... But here's what we're looking for. The p-value. I'm reading 1.574, ... But then I got this e -4. All right, that's my p-value. Now, when you see something like this with an e, this is a probability. You know it can't be 1.5. So you're looking right over here directly. E. All right, this is a calculator's way of saying scientific notation. So what you're saying is the p-value is 1.57 times 10 to the, what happened here? Times 10 to the -4. Now, scientific notation just moves decimal points around. So to get that decimal point right there, we must have moved it 4 places to the right. The negative means it went to the right. So to get it out of scientific notation, move it 4 places to the left. So I'm going to take this decimal point and go 1, 2, 3, 4, right? So it's going to look like this. P is equal to point, all right? Now I'm going to move it here, right? 1, and then I need 3 zeros. 1, 2, 3 zeros, and I get to 157. Or how about this? P equals 0.000. I got a 5 here, so in statistical rounding we go up. So I get a 2. There's my p-value, 0.0002. Now we have our choice of alpha. Suppose we choose alpha to be 0.01. Okay, then let's compare p and alpha. Find out what it is we're going to do. Reject or not reject. So p is 0.0002. Alpha is 0.01. Now 0002 is less than 01. So I'm seeing a less than. And when I see less than, I'm thinking small, but we're dealing with small p's, small probabilities. So this is a small probability. So the probability of actually seeing, right, the probability of seeing, I'm over here on the left, the probability of seeing this data given that there's no correlation, right, given this, right, the probability, here's what we're saying, the probability of seeing this data given this is true, that is very small. And if I'm thinking small, I'm thinking this is an unlikely event. And I don't think I see unlikely events. So I am going to reject H naught. And then we can write our conclusion. At alpha equals 0.01, this sample indicates there is enough evidence to suggest there is a correlation between, okay, let's say barometric pressure and wind speed. Now, in fact, while we're doing this, we could have done this. You see what we did up here? We tested that there was no correlation, but what did our correlation look like? I'm just going to go back a page and a page. Look at our correlation. Didn't it seem to you to be negative? So what if we say, instead of that there's no correlation, I'm going to go back to where we were, what if we run this test? What if we run a test that says, okay, H naught still states, what if we state now that rho is negative, right? We have a negative correlation. That's our alternate. Versus that rho is, now what? What's the opposite of less than 0? Greater than or equal to 0. So now we're going to run the less than test instead of not equal test. So now this is simple for us now. Just go back to stat, test, right? Stat, tests. Now, you've got your data in already. The only thing you have to change is, all right, so we still have the X is L1, the Y list L2, and now we're going to tell, okay, frequency is 1. But now what I want is my rho to be, okay, not equal to 0, but this time less than 0. That seems like a reasonable thing. All right, so get that, get your cursor down here, and then calculate. Let's see what happens. So when I calculate this time, I get a p-value of, okay, 7.87 ... e negative 5. Okay, now as soon as I see the 7 point something, I know there's an e because probability can't be over 1, can't be a 7 point something. So p is equal to get the decimal point, okay, well actually it's equal to what? 7.87 times 10 to the negative 5. And to get that decimal point right there, we must have moved it 5 places to the right. So let's get it out 5 places to the left. So p is equal to point, I need 4 zeros, and then 7, 8, what if I just round it off to 8? Okay, there's our p-value. Now that is really small, right? This is what? This is tenths, hundredths, thousandths, 10,000ths, 100,000ths. This event, 8 over 100,000. So what we're saying here is that if rho, the coefficient of correlation, was really suppose greater than or equal to 0, no correlation, right? No correlation. Suppose there was really no correlation. How often would we see? We would see our data. I can't write here. We would see our data 8 times in 10,000 trials. Okay, now that is an unusual event. This is unlikely, so we would reject H naught. Again, we're going to reject H naught, so we reject rho equaling 0. All right, We reject that there's no correlation. Reject no correlation. So we would say at alpha equals 0.01, this sample indicates there is a positive correlation between barometer reading and wind speed. And it just occurred to me back over here, and it's probably bothering you, back over here I said 8 times out of 10,000. Well, it's not. It's 8 times out of 100,000. Now, let's do one more thing while we're in this section. While we're here, we just got our calculated results when we tested this one here, right, where we were testing H naught states that rho greater than or equal to 0. H sub A states that rho is less than 0, that we have a negative correlation. All right, this is what came up on my calculator. First thing that came up is this y equals a plus bx. Now I'm going to change that notation just a little bit. I'm going to write y hat equals a plus bx. So just what is this? This turns out to be our regression equation. Well, this really goes to our question number 2, which is, question number 1 was, first of all, is there a correlation? Well, in our problem right here, we've just answered that. We are rejecting this and we're going with this, that there is a negative correlation. Then the second question comes up is this: if there is a correlation between the variables, how can we express it mathematically? How can we write an equation that predicts one from the other? So do you remember back in algebra, you had this? We all remember this one. Y equals mx plus b, where this is the slope of the line and this is the y-intercept. All right, this is where the line crosses the y-axis. So maybe you had something like this. Here's a line, crosses the y-axis right there. That's b. And the slope would be this. If you make a 1 unit change here, you would go down m units over here to get back on the line. So the slope-intercept form. Now, y equals mx plus b. In statistics, it's just turned around and we're going to write a y hat over it. And instead of mx plus b, we're going to write a plus bx. So the m is like the b and the b is like the a. All right, but if I write this, y hat equals a plus bx, that's the slope. And the number out there by itself, that constant, that is the y-intercept. The calculator has given us a lot of important information here, a lot of useful information. Over here on the very left, you might have to scroll down a little bit, but you'll see the values of A and B. Now, the calculator is telling me that A is equal to 1496.78 and B is negative 1.44. Now, let's substitute into our equation, regression equation, right here. It is y hat equals a plus bx. So y hat is equal to a, which was 1496.78, plus b, but b is negative 1.44x. There is the relationship between x and y. So if I know a value of x, if I'm given a value of x, which was what? X was what? That was a barometer reading. If I'm given a barometer reading, I can multiply it by negative 144 and add 1496.78 and get out a pretty good estimate for the wind speed of that cyclone. But I don't have to do any computing. There's a lot of important information given right in front of us if we just know how to read it. That right there, that 1496.78, that's the y-intercept. Now that's the value of y where x is 0. Come up here, I'll draw a little picture. All right, here's a line that crosses the y-axis right there. Now that is b, or in our case that's a. I'll just say it's the y-intercept. X is 0, right? X is 0. So I know the line crosses the y-intercept, the y-axis when x is 0. So all I have to do is look down here at my equation and say, oh, when x is 0, that's my start values. Like I start here, and then x gets bigger or smaller. So I start there. That's a start value. So when x is 0, when the barometer reading is 0, we've got about 1,500 miles per hour for the speed of that cyclone. What about this? Well, that's the slope. And what is the slope? Well, we usually use the letter m, but what's the slope? It's a fraction, right? The slope's always a fraction. It's the vertical change on the top, the horizontal change on the bottom. So if I look at this number without doing any computations, negative 1.44, that's equal to negative 1.44, just make it a fraction, over 1. That tells me that if I'm at any point on this line, if I go over any point on the line, just pick a point on the line. If I go over 1 unit, right, horizontal, if I go a horizontal unit to the right, positive 1, what do? I go down, right, down 1.44, right? So for every increase, 1 unit increase in the barometer reading, the wind speed goes down by 1.44 units. Okay, we've done a whole lot in this unit. Let's put an end to this right here. But now you could probably just be finished with this section because you know how to get R, you know what it means, and you know how to get the regression equation, and you know how to compute with it, and you know what it means. I'm going to finish up regression and correlation in the next section by just talking about where this equation comes from, right? We just read it off on the calculator that I'm up here at the top right. Where does that y hat equals a plus bx, what does that mean? Where did it come from? We'll talk about that and get a picture so you have a feel for what that equation does.